We stand on the cusp of a new space age. Private companies are launching rockets, their fiery plumes painting streaks of ambition across our skies. The dream of space tourism is becoming a reality. People are strapping themselves in, paying for a few precious minutes of weightlessness, gazing down upon the delicate blue marble of our home world. It's an experience that changes you. It's only natural our imaginations wander further. If we can touch the edge of space, why not the moon? If the moon, why not Mars? And if Mars, why not a planet orbiting another star? The allure of exoplanets is undeniable. For millennia, we have looked up at the stars and wondered, are we alone? Now, thanks to powerful telescopes like the James Webb Space Telescope, we know that the universe is teeming with worlds beyond our own solar system. We've found thousands of them. Some are scorching gas giants, others are frozen ice worlds, but a precious few orbit within their star's habitable zone, that temperate region where liquid water could potentially pool on a rocky surface. The thought of visiting such a world, standing under an alien sun, breathing alien air, is perhaps the ultimate expression of human curiosity and our innate drive to explore. This grand vision fuels our science fiction, our art, and our deepest aspirations for the future of our species. We imagine interstellar cruise liners gliding through the cosmos, their passengers sipping cocktails while watching nebulae drift by their windows. We envision stepping onto a world with two suns in its sky or walking through forests of bizarre alien flora. These are powerful, inspiring dreams. They speak to the adventurer in all of us, the part that yearns to see what lies over the next hill, or in this case, across the next light year. But dreams are one thing. The laws of physics are another. The gap between visiting Earth's orbit and visiting an exoplanet is not a step. It is a chasm. A vast, dark, and profoundly difficult gulf to cross. To understand why exoplanet vacations remain firmly in the realm of science fiction, we must first confront the sober, humbling reality of cosmic distances and the fundamental limits they impose upon us, the fragile inhabitants of a single, small world. The universe is vast in a way that our minds struggle to grasp. We use units like miles, kilometers to measure our world, but these become laughably small when we look to the stars. The distances are so great we invent a new yardstick, the light year. A light year is how far light travels in a year. That's nearly 6 trillion miles, 9.5 trillion kilometers. It's a number so large it loses everyday meaning. Let's consider our nearest stellar neighbor, Proxima Centauri. It hosts at least one planet, Proxima Centauri b, a rocky world slightly more massive than Earth. It's the closest known exoplanet. How far away is it? About 4.2 light-years. That sounds small, just over 4. But remember what that means. Shrink the cosmos to scale. If the sun were a grapefruit in New York City, Earth would be a grain of sand about 50 feet away. Mars would be another grain of sand about 75 feet away. Proxima Centauri b, another grapefruit star system with its grain of sand planet in San Francisco. That's the distance we mean. This is the tyranny of distance. It's not just a big number, it's a fundamental barrier. Space between stars is not empty, it's emptier than any vacuum on Earth, cold, dark, lonely, stretching for trillions upon trillions of miles. Our entire history, every war fought, every cathedral built, every love story told, has happened on a tiny speck in a cosmic ocean. To dream of crossing that ocean takes imagination. To actually do it requires confronting this staggering, almost spiritual sense of scale. So the nearest exoplanet is incredibly far away. Our next logical question is, how fast can we go? Our current spacecraft, wonders of engineering though they are, move at what can only be described as a cosmic snail's pace. The Parker Solar Probe is the fastest object ever built by humans. By using the sun's own gravity to slingshot itself, it has reached incredible speeds of over 430,000 miles per hour. That's fast enough to get you from New York to Los Angeles in about 20 seconds. It's an astonishing achievement of human ingenuity. Yet even at this blistering, record-breaking speed, the journey to Proxima Centauri b would be an exercise in futility. If we could point the Parker Solar Probe in the right direction and send it on its way, how long would it take to cover those 4.2 light-years? The answer is humbling. It would take approximately 6,600 years. 6.5 millennia. That's longer than all of recorded human history. The pyramids of Giza would not yet have been built when the mission launched, and what would our civilization even look like upon its arrival? The travelers would not be tourists. They would be relics from a forgotten past. Our fastest chemical rockets, the ones that lift our astronauts into orbit, are even slower. The Apollo missions to the moon traveled at about 25,000 miles per hour, A trip to Proxima Centauri b at that speed would take around 114,000 years. Generations would be born, live their entire lives and die aboard the ship. The destination would become a myth, a legend passed down through 100 generations locked inside a metal can. It's simply not a feasible way to plan a vacation. Our current technology, the pinnacle of our achievements, leaves us hopelessly stranded in our own cosmic neighborhood. Let's imagine we could build a ship capable of making the journey to Proxima Centauri b in a reasonable time frame, say 40 years, a single human working lifetime. To achieve this, the ship would need to travel at about 10% of the speed of light. The next question becomes, where do we get the energy to make it go that fast? The answer reveals another barrier. The energy requirements are astronomical. To accelerate a spacecraft, even a relatively small one, say the size of a large passenger jet, to 10% of the speed of light would require an amount of energy that defies easy comparison. It would be more than the total amount of energy consumed by the entire human civilization in a single year. Think about that. Every power plant, every car, every light bulb, every factory. Running for a full year would not generate enough energy to launch this one mission. We would have to dedicate the entire energy output of our planet for a significant time just to get the ship up to speed. And that's only half the problem. Once you arrive at your destination, you don't want to just fly by at 10% of the speed of light. You want to stop. To slow down from such a high velocity requires just as much energy as it took to speed up, so you would need to carry all that braking fuel with you, making the ship heavier, and requiring even more energy to launch. This vicious cycle, the tyranny of the rocket equation, is a brutal master. It dictates that for every pound of payload you need many, many more pounds of fuel. That's why new propulsion ideas are so critical, but also why they remain so theoretical. The energy bill for an interstellar trip is so high that it's not a check our current civilization can write. Even if we could solve the monumental problems of distance and energy, a third equally daunting challenge would remain: the human body. We are creatures of Earth, exquisitely adapted over millions of years to this specific environment. We're built for its gravity, protected by its magnetic field and nourished by its biosphere. Interstellar space is the most hostile environment imaginable, and sending a fragile human being through it for decades or centuries is an unprecedented experiment. First, there's the issue of radiation. Outside Earth's magnetosphere, space is flooded with high-energy cosmic rays. These are tiny subatomic particles, remnants of distant supernovae, traveling nearly at the speed of light. They can zip through a hull and human cells, shredding DNA and raising cancer risk. Shielding for decades would need immensely thick, heavy materials, which worsens the energy problem. It's a cruel paradox. Protection makes the journey harder to start. Then the problem of biology over time. How do you keep a crew healthy for 40 years or for generations? Long-term zero or simulated gravity effects are not fully understood. Bones lose density, muscles atrophy, the cardiovascular system weakens. We'd need closed-loop life support to recycle air, recycle water, and recycle waste for centuries. We'd have to grow food, manage disease outbreaks, and ensure genetic health in a tiny artificial world. Finally, consider the mind. The psychological toll of confinement millions of miles from anyone would be immense. The crew would know there is no rescue, no turning back. They'd watch Earth shrink to a pale blue dot, then fade to nothing. How do you select a crew? How do you maintain morale, purpose, and social cohesion for decades in the dark? The vast, empty quiet of interstellar space could threaten the human spirit more than any radiation storm. Let's add another layer of complexity to our hypothetical journey. Piloting a ship through the solar system is already a masterclass in orbital mechanics, but navigating the interstellar void presents a whole new set of dangers. The space between stars is not perfectly empty. It's actually a dusty, clumpy place filled with grains of sand, tiny pebbles, the occasional rogue rock, all moving at incredible relative speeds. At the velocities required for interstellar travel, even a speck of dust becomes a lethal projectile. Imagine your ship is traveling at 10% the speed of light. At that speed, colliding with a particle as small as a grain of sand would release the energy equivalent of a powerful bomb. The impact would be catastrophic, capable of vaporizing a section of the ship's hull in an instant. A pebble-sized object would be an extinction-level event for the mission. To navigate this cosmic minefield, the ship would need an incredibly advanced sensor system to detect these tiny objects from far away, and a powerful deflection mechanism, perhaps lasers, magnetic fields, to push them aside. Furthermore, you aren't aiming for a stationary target. The exoplanet you're trying to reach, Proxima Centauri b, is in motion. It's whipping around its own star, and its entire solar system is moving through the galaxy at hundreds of thousands of miles per hour, on a different course and speed than our own sun. You can't just point your ship at where the planet is now, you have to aim for a precise point in space where you predict it will be decades or centuries in the future. It's like trying to throw a dart in New York to hit a moving penny on the edge of a spinning record in San Francisco 40 years from now. The level of precision required for such a maneuver is staggering. A tiny error in your initial trajectory calculation, a miscalculation of your velocity by just a fraction of a percent, would mean missing your target by millions of miles. After traveling for decades across 25 trillion miles, you could arrive at your destination only to find an empty patch of space, with the planet you sought being a distant, unreachable light. The celestial mechanics are unforgiving. The margin for error is effectively zero, and the consequences of failure are absolute. Given these colossal challenges, it becomes clear that interstellar vacations are not on our immediate horizon. This doesn't mean the dream of space exploration is dead, it simply means we need a more realistic roadmap. The journey to the stars will not begin with a giant leap, but with a series of careful, deliberate steps. We must learn to walk before we can run. The first steps will happen much closer to home, within our own solar system. This is where space tourism will truly begin and evolve. The first destination is, and will continue to be, low Earth orbit, the front porch of space. Tourists can experience weightlessness, feel the overview effect, and witness Earth's curvature and fragile atmosphere. The market is already emerging. Private companies offer short flights to the edge of space. Over time, these trips will get more accessible and affordable, leading to orbital hotels. Guests could stay days or weeks, conducting research or just enjoying panoramic views. Next, a return to the moon. A 3-day journey in cosmic terms. The moon gives a true off-world experience, a different ground beneath your feet, 1/6 of Earth's gravity, and Earth hanging huge in the sky. We can envision lunar bases for scientific research and later for specialized tourism. Picture an Earthrise from a crater rim, or a pressurized rover rolling across lunar plains. Once we master living and working on the moon, we'll be ready to aim for Mars. Mars is far harder, 6 to 9 months in transit and a much harsher environment. Yet it offers a thin atmosphere, weather, and a history that may hint at past life. Building a permanent, self-sustaining presence on Mars will be the great project of this century. Achieve that, and we become a multi-planetary species. These are the real, tangible next steps in our cosmic journey. So, if human travel to the exoplanets is off the table for the foreseeable future, does that mean we must abandon our dream of exploring them? Absolutely not. It simply means we need to send the right explorers for the job. For the daunting task of crossing the interstellar abyss, our best pioneers won't be flesh and blood, but silicon and steel. The near future of interstellar exploration belongs to robots. Robotic probes are the perfect emissaries. Robots aren't constrained by human frailties. They don't need to eat, drink, breathe. They are unbothered by decades of isolation or by the psychological pressures of a long voyage. Most importantly, they're far more resistant to deep space radiation. We can build them to withstand the cold, the vacuum, and cosmic rays. A robot doesn't get cancer. That lets us design missions that are longer, more daring, and far less complex. We can make probes incredibly small. Breakthrough Starshot imagines fleets of tiny nanocrafts to our nearest star. Wafer-thin probes weighing only a few grams, attached to ultralight sails. An Earth-based laser array would focus a beam on the sails, accelerating them to tilde 20% of light speed. At that speed, they could reach Proxima Centauri in just over 20 years. They could fly through the system, snap pictures, collect data, and beam it back to Earth. It's audacious and achievable within our lifetimes. We wouldn't be going there ourselves, but we'd extend our senses across light years. We'd receive the first close-up images of a world around another star. We'd analyze its atmosphere, map its surface, and search for signs of life. These robotic emissaries would be our eyes and ears in the cosmos, letting us explore without risking human lives. They are the logical next step in our quest to know the universe.